how to explain about simple harmonic motion. So we start with a spring and it's hanging at rest. The spring is currently at equilibrium. There's not much interesting happening. So the next thing we'll do is let's put a mass on our spring. We've hung a mass from the spring. We've allowed it to come to rest, so it's at equilibrium again. So now it's at a new equilibrium position. This is where the spring has a net force of 0 because it's at equilibrium. If we were thinking about a free body diagram, we know there's a spring force holding it up, and that's given by Hooke's law, F equals kx. And there's the force due to gravity pointing down, F equals mg. Since it's at equilibrium, and we know it's at equilibrium because it's not moving, then the net force would be 0. So if we measured how much it stretched by, we would know x for our F equals kx. Could set it equal to mg, and then we could find our spring constant. Okay, so that's the standard stuff. There's the background information. What about simple harmonic motion? Well, if we push that mass a little bit, let's see what happens to it. So I displace the mass downwards by a couple of centimeters and I let it go. So what we see happening is that the mass bounces up and down. It's oscillating. It oscillates about the midpoint. It oscillates about that equilibrium position. So it goes up and down, back and forth around that position. It has some maximum position. There's a maximum distance it will stretch from the equilibrium. That's called the amplitude. We see that the velocity is not constant. Sometimes it's moving up and sometimes it's moving down. When it switches from moving up to moving down, it turns around. That's a turning point. There it has velocity equal to 0. We see that it moves the fastest when it's in the middle, when it's going through the equilibrium point. So we see that the velocity is not constant and the position is not constant. So things change back and forth. This kind of motion is known as simple harmonic motion. The mass on the spring is sometimes called a simple harmonic oscillator. And this kind of motion occurs whenever we have a restoring force. A restoring force is any time we have a force that pulls an object back towards an equilibrium. If the mass is pulled down below the equilibrium, then the spring force wants to pull it back up. If the mass is pulled up above the equilibrium, then the spring force wants to push it back down. The spring force always pushes or pulls it towards the equilibrium, so that's called a restoring force because it wants to restore it to the equilibrium. Anytime we have that kind of a force, the resultant motion after we give it a little push is going to be simple harmonic motion. So that covers what simple harmonic motion looks like as an experiment. In the next video, we'll analyze the forces and we'll use Newton's second law to write the equation of motion for a simple harmonic oscillator.